Okay, so I will discuss the emergent universe scenario in quantum gravity in its general conceptual terms first, and then in one specific research program. And more precisely, I will focus on the question of what is cosmology, cosmological dynamics, from the point of view of an underlying quantum theory of gravity in this emergent universe scenario. So let me first clarify what I mean by emergent space-time. So in general relativity, space-time notions are already challenged, as many of you know very well. And the space-time structures I refer to are the topological manifold, the continuum metric field, and additional matter or gauge fields that can be used to define the notions of time evolution or local regions. So, and the reason why space and time notions are challenged is basically different variance. Is the fact that because of the symmetries of the theory, no preferred time or space directions are allowed, and notions that are mathematically like manifold points or paths on the manifold, and the values of fields or their functions at specific points in the manifold do not really have a physical meaning per se. They have to be given a physical meaning by identifying what you mean by a point or a local region or a path through the use of the additional degrees of freedom your theory may contain, that is the matter fields. So in a relational way. So when you ask how this carries on to a quantum theory of gravity and space-time, it depends very much on which perspective you take. If quantum gravity is just a quantum theory of the gravitational field, then the problem, which is already very difficult, of course, is just to quantize all these kinematical and dynamical structures. And the only way, however, in which space and time have disappeared even more in the quantum theory than in the classical one is simply that the usual notions of space and time are crucial for our interpretation and use of quantum mechanics. And because they were lacking in general relativity, we are not really sure how to interpret and use the corresponding quantum theory. But the origin of the disappearance is the same, different variance. And we didn't change the degrees of freedom of the theory. We're still dealing with the continuum metric and matter fields, just at the quantum level as operators on some Hilbert space. So the fact that you didn't change the fundamental degrees of freedom is what marks the difference with other perspectives. And before I go in towards discussing this other perspective, I emphasize again that both at the classical and quantum level, the one way out of the problem of how to define notions of space and time in presence of different variants is the relational way, and I'm going to use it later on. That is to define what you mean by points and directions and so on, with respect to internal degrees of freedom, physical degrees of freedom of your system. So the fact that quantum gravity should be understood as just quantized general relativity is challenged by several hints that we have from existing physics. So first of all, there are several results in classical and semi-classical gravitational physics that suggest a breakdown of the continuum framework and of effective field theory itself. And I listed a few, and some interpret in this way the presence of space-time singularities in GR as a breakdown of the continuum description itself, and others interpret in this direction black hole thermodynamics with a simple logical argument that, heuristic of course, that if black holes, which are nothing else than regions of space, have an entropy, they must have some microstructure, which basically implies that this space itself has a microstructure. And there are other perspectives suggesting the same shift in point of view concerning space-time and quantum gravity. So already from these few hints, you would expect that to some extent the notions of continuum space-time will disappear in a more complete theory. And by the way, sorry, none of the pictures in the talk will be taken from the real world. And the other set of hints suggesting that a different perspective on quantum gravity is needed come from existing quantum gravity approaches. Even the most conservative ones end up suggesting microscopic degrees of freedom or microscopic structures for a quantized space-time that are just not spatiotemporal in the sense of corresponding directly to quantized fields. So they suggest something more in terms of non-spatiotemporal atoms of space. So if quantum gravity is really not about quantizing GR, but about understanding the microstructure of space, then the tasks are, on the one hand, to identify what the atoms of space could be, and even more difficult, to show that from this microscopic non-spatiotemporal description, the usual notions of space, time, geometry, and so on emerge with the appropriate modified GR dynamics. And this second set of challenges is what I will focus on in the second part. So in the second perspective, you expect the gravitational field to be the result of the collective dynamics of these microscopic atoms of space. So to be really the result of coarse graining, the result of some emergence process in the theoretical, not dynamical sense, not temporal sense. And this has immediately quite an implication for the way we conceptualize quantum gravity in the space of theories. It means that we have to go beyond the Bronstein cube, which is where many people see quantum gravity with respect to other theories, towards something like a Bronstein hypercube, because we added another direction in our theory space, which is the direction in which you have a set of degrees of freedom and you increase their number. And this is regardless of whether there is some Newton's constant, so there are some gravitational aspects in the story, whether the microscopic degrees of freedom are quantum or classical, the h-bar direction, or whether they are in some generalized sense relativistic or not, that's the c direction. So in a way, it's really enlarging the theory space to bring in also the main lessons from condensed matter theory, which doesn't introduce new fundamental interactions, but introduce a new fundamental way of thinking about the world in which emergent behavior, collective dynamics becomes crucial. And this n direction is the direction in which, as I said, you increase the number of fundamental quantum interacting degrees of freedom, and that's the direction where emergence takes place in all the systems we know, I would say. So I will distinguish, the classical limit from what I call the continuum limit. And two directions do not commute in general. And for most systems we know, they do not commute. One example would be quantum fluids. If you took your theory of quantum atoms for a Bose condensate, for example, and you first take a classical limit, then you will never recover superfluidity at the macroscopic level, so in the continuum limit. You first have to take a continuum limit, you get the full macroscopic set of properties, and then if you want, you can take a classical limit in which you forget about the quantum pressure, you forget about some quantum aspects of the fluid, and you get standard hydrodynamics. So this is one example. So I will claim that the same is true for space-time. The first point, space-time dissolves into non-spatiotemporal degrees of freedom in quantum gravity, from which space, time, and geometry have to emerge. That this means that there is a new direction to explore, and in particular, we should be able to control in our theories of quantum gravity the regime of many fundamental degrees of freedom. So I cannot talk about scales in the sense of microscopic, small distances or large energies and so on, because these are geometric notions. The only notion of scale will be the number of degrees of fundamental degrees of freedom. The second main point I made up to now is that for all we know, when we have quantum interacting degrees of freedom, the physics of few degrees of freedom is very different from the physics of many degrees of freedom. So the step along the n direction is usually highly non-trivial. Okay, now this would be just nice words, if not for the fact that indeed quantum gravity approaches are suggesting microscopic degrees of freedom of this generalized, non-directly spatiotemporal type. Loop quantum gravity is one example in which at the end of a long story that started as conservative as possible, meaning I just try to quantize GR by canonical methods without introducing any new set of degrees of freedom or new symmetries or anything weird, well, you end up with quantum states where you lose any track of continuum fields, geometric or matter fields, and you have graphs labeled by algebraic data as the microstructure of space, which in turn you can interpret also in terms of cellular complexes, I mean discrete building blocks in the sense of tetrahedra of extended discrete spaces. And the same is true at the dynamical level with the notion of spin foam. Is again just one higher dimensional purely combinatorial and algebraic object that should replace the usual notion of space-time manifold in the theory. So you, in one word, you replace at the end of the process fields and continuum manifolds with graphs or cellular complexes, purely combinatorial objects, labeled by purely algebraic data. And you can, a related approach is the group field theory framework, which is what I'm going to focus on in the specific example I will discuss later. So it's the same type of degrees of freedom organized as field theory, a formal field theory on some auxiliary space, the group manifold. And there's no point in going into details, but it's a field theory in the sense that there is a Fock space that you create, annihilate the fundamental quanta, and you're dealing with the same type of degrees of freedom as in loop quantum gravity, because the fundamental quanta are like little pieces of graphs. A generic graph can be split into vertices with open links, and then you glue them to form the extended graph. And each individual vertex with open link is a quantum of this field theory, this more abstract generalized field theory called group field theory. And it has the corresponding simplicial interpretation, in the sense that to each such vertex you can put in correspondence a fundamental tetrahedron, a little cell, again, a purely combinatorial structure. And just like you can glue together the vertices to form larger pieces of a graph, you can glue together tetrahedra to form larger pieces of a simplicial lattice. This type of states will be many body states in this field theory with the wave function and so on. So group field theory is just a quantum field theory of spin networks, if you want to interpret it intuitively. It has, you write down an action that defines a dynamics, a partition function. All of this doesn't use any notion of continuum fields or geometry. And you can expand it in Feynman diagrams, the partition function. Each Feynman diagram is a cellular complex one dimension higher. So if you had tetrahedra, three-dimensional simplicial building blocks, the Feynman diagrams, which are the interaction processes of such tetrahedra, will be four-dimensional simplicial lattices, and so on in different dimensions. And the Feynman amplitudes can be written down. The probability amplitudes associated to each such possible interaction process can be written down as simplicial gravity path integrals, so discretized gravity path integrals or spin foam models. This is just to connect to other approaches, in particular to the main ideas of dynamical triangulations and quantum regge calculus, which are two other approaches to quantum gravity. The sum over triangulations is here the sum over the Feynman diagrams, all the possible interaction processes of the fundamental degrees of freedom of the theory, of the field theory. Okay, the details of the formulas are not so important at the moment, but the message of this part is just that you can have very abstract, purely combinatorial and algebraic degrees of freedom underlying space and space-time. You can organize them and their dynamics in the language of a field theory, and by doing so, you bring together ideas from and mathematical structures from other approaches, which is some added value. And the main added value of this reformulation is that you can really apply tools from standard field theory, despite the fact that you are in such background independent, much more abstract context. And here's a slice of the Bronstein hypercube in this particular case. You can start with a few quantum gravity degrees of freedom, in the quantum regime, so very simple spin network graphs, or very simple quantized lattices. You can take a classical limit, but you're going to get just a few classical lattice gravity degrees of freedom. Their dynamics is going to be something like a regge calculus action, some discretized gravity action. You still have to take the continuum limit to get GR. But you can take the same continuum limit in the quantum theory, and that is really what the quantum field theory framework is useful for. Study the collective behavior of many particles, many quanta, remaining at the quantum level. And I emphasized already that these two limits have no reason to commute. So it's usually, I would say, it's better to find this will be full quantum gravity, and then check if once you control the large number of degrees of freedom, the classical limit gives you GR, continuum GR. Okay, so I think I already made most of those points. Here I'll skip a few couple of slides, or at least I will be very quick. So in the first aspect of this taking the continuum limit in full quantum gravity, which has to do with the emergence of space-time at the kinematical level before trying to extract physics, can be done using results from several of the approaches that I mentioned. And I claim that already at this level you have to describe the physics of your theory through relational observables. The second aspect is really to check that when you take the continuum limit at the dynamical level, you may encounter different phases. Every system we know with many degrees of freedom that are quantum and interacting organizes itself in different phases. So we should expect the same in quantum gravity, whether loop quantum gravity or spin-form models or group field theory, and there has been a lot of work in the field for realizing the phase diagram of fundamental quantum gravity models. And this raises, from a more conceptual point of view, an interesting issue, which is suppose that we are lucky enough that there is indeed for our models a nice geometric phase in the continuum limit, meaning a phase that we can describe approximately with some smooth manifold and metric field and so on. This is the lucky part. We have done a lot, and we can maybe show that we find GR here. But what about the other phases? Are they physical or just mathematical artifacts and so on? And we have no a priori reason to judge them as pure mathematical artifacts just because they're not geometric. If the fundamental degrees of freedom, we interpret them in more realistic terms as really the fundamental degrees of freedom of space or of the universe, well, it's the same type of degrees of freedom here. So, and then the other question is whether there is anything like a phase transition. So if there are different phases, there will be mathematically phase transitions, and the question is whether we want to give a realistic interpretation to them. Are they physically processes in the universe, and what do they correspond to? And the suggestion could be that just like molecules condense into liquids, that can be described macroscopically by fields and smooth structures. In the same way, this fundamental, discrete, atomized degrees of freedom of quantum space can condense to form some still quantum but smooth or continuum space-time and geometry. And again, I'm not talking about the classical limit here. It's the continuum limit that I'm discussing. So this is another place where the notion of geometrogenesis has been developed. And a tentative interpretation is a cosmological one. I mean, the transition from a non-geometric to a geometric phase is what replaces fundamentally the Big Bang singularity in early universe cosmology. Okay, now I discuss more precisely about, more specifically about how are we supposed to understand cosmology first, and then how we are supposed to extract cosmology from the fundamental theory within this conceptual framework of emergent space-time and collective dynamics involved in it. So there are, just like there were 2 points of view of what quantum gravity is, there are also 2 points of view related to them on what cosmology is supposed to be. So you can say that it's the dynamics of spatially homogeneous geometries and matter fields. So you take special configurations of continuum fields, which are homogeneous, so very simple, and you just describe their dynamics. This is what we do in classical GR when we just say cosmology is the Friedmann equation. At the quantum level, this point of view would suggest that you take those special configurations of general relativity in the continuum, which are highly symmetric and very simple, and you quantize them. You obtain a very simple quantum theory of those continuum configurations. This is quantum cosmology, which has a long history of successes and failures. But of course there are a lot of interesting results, especially in recent formulations of it, like loop quantum cosmology. But you're always left with the question, is this just a toy model, or it does indeed capture true physics of an underlying quantum theory of gravity? Because of course the idea of restricting to some configurations and quantizing raises the doubt that the process of quantization will not commute with a reduction to a few degrees of freedom. So you're not really you're not really controlling whether your truncation doesn't lose important physics. The second point of view that is more in line with the emergent space-time picture, and I would say is actually implied by the emergent space-time picture of quantum gravity, is that cosmology has to be the result of coarse-graining the gravitational degrees of freedom at the classical level up to global quantities only. So cosmology is the effective dynamics of a few very special observables obtained after coarse-graining of the set of gravitational degrees of freedom. I would say that to some extent everybody would agree that this is true. The point is that it's technically very difficult to do it, and it's unclear whether you really need to do it in the classical theory. But in the quantum theory, this seems to be, to me, a necessity if you really believe that fundamental degrees of freedom are not geometric, are not continuum fields. Because there's no place where you would do symmetry reduction there. So what is homogeneous cosmology from the point of view of full quantum gravity? You could say that you have to focus on a few macroscopic, more global type observables, which have to be understood as suitably defined averages over fundamental degrees of freedom. You are expected to be close enough to equilibrium in order to be able to deal only with those macroscopic observables. And also because of this, you expect that it's going to be valid if you are insensitive enough to the microstructure, to the underlying microstructure. Now, if this is what cosmology is, then you ask, okay, but what if I'm near homogeneous? Well, it means that you are introducing more observables, but you're still close enough to equilibrium and insensitive enough to the microstructure. If you start being really far from the homogeneous setup, then it means that you have enough observables to reconstruct a full-fledged local effective field theory, And then you really don't know if you are supposed to be close to equilibrium or far from it and still insensitive to the microstructure. The point is that this is basically the definition of the hydrodynamic regime of any microscopic theory, condensed matter or some more exotic stuff. So let me make a short digression to remind a bit more about hydrodynamics, because then I will use the same type of ideas in the quantum gravity system. So I assume that we more or less all know what hydrodynamics is, but again, is the description of the system close to equilibrium. For exact equilibrium, thermodynamics is enough. Close to equilibrium, there is still some dynamics, but is only at this very global level of description, very macroscopic. Is concerned with a very small number of macroscopic quantities which correspond to large averages over the microscopic degrees of freedom. So these are all trivialities, so it's not that we all know this, but keep in mind these basic points, because I'm going to apply the same basic ideas to quantum gravity models. So key variables at this level of description are densities of conserved quantities, or quantities resulting from broken symmetries. For simple fluids, you can get a closed system of equation for the single particle density and for the fluid velocity, and these are the hydrodynamic equations. In general, the computation of these average quantities is extremely complicated, but in practice, for most observables, it doesn't require the full knowledge about the microscopic system, but just the computation of reduced densities. For example, if you have a many-body Hamiltonian like this, these are just a bunch of n particles interacting through the electromagnetic field with each other, and some other potential. The internal energy is just the average of the Hamiltonian and can be expressed just in terms of this one-body density and a two-body density. So you don't need the full partition function of the microscopic atoms or molecules. You just need two functions which have a domain which is just a one-particle phase space and a two-particle phase space. Of course, computation of those densities can be complicated, but in particular for one-body observables, those that are really like extensive, they're just the sum of the microscopic contribution from each particle, everything is even simpler, because you only need the one-particle density, which is exactly what becomes the fluid density in the hydrodynamics. So if you know by a sheer luck all the microscopic details encoded in some density functional, here for all your n particles, you know exactly everything about all of them, then you just have to take this integral. At least formally, you just reduce to information about a single particle, what looks like a single particle density. Or normally you have to do it with a lot of approximations, of course, or assumptions. But at the end, if you have this quantity, that's the only thing that matters for most observables in the hydrodynamic macroscopic description. So this is the key message. In some cases, like a Bose condensate, even starting from the exact atomic theory, this is the field theory for bosonic atoms, with some potential, some two-body potential. The extraction of the macroscopic one-particle density is very simple, under the assumption that you are in a condensate phase, that the interactions are weak, and a bunch of other conditions. But you can really follow the analytic path from the microscopic description, assuming that you are in a simple state, which is a condensate, about which I will say something more in a second, and you just extract the corresponding hydrodynamics, the corresponding hydrodynamic equation. So this is a condensate which can be seen as an infinite superposition of n particle states with n from 0 to infinity, which is very special. It's such that all particles have the same wave function, phi 0. This is an exact condensate. It's the simplest possibility you can imagine for a condensate. All the particles have exactly the same quantum state captured by a single wave function phi 0. This wave function, therefore, describes collectively an infinity of degrees of freedom, of macroscopic degrees of freedom. And is exactly what plays the role of the one particle density in the hydrodynamic description. You just write it in terms of the modulus and a phase, and the modulus is the one particle density, the density of the fluid, and the phase, you use it to compute the velocity of the fluid, which are the two hydrodynamic variables. And this equation can be written then in standard hydrodynamic form, is the Gross-Pitayevsky hydrodynamics for a condensate in this simple approximation. Okay, so all this is analytic. Okay, the only point I want to emphasize here, there are 2 points. One is what I just said. In some cases, the construction of hydrodynamics from the microscopic theory is a bit more direct and requires assumptions, but is still analytic. And the second point is that this is an example in which the quantum features are crucial. The previous state that I wrote, I don't want to go back, the condensate just does not exist as a possibility if you take a classical limit at the level of the particles. Okay. Okay, now suppose that we want to play the same game.
Sorry, it's just one point. There's also another limit to take for a Spacetime equation where the quantum potential drops out. It's a different type of Hypercube.
Sure, no, it's a classical limit at the hydrodynamic level.
Yeah, the equation.
So this is the case, this is exactly one of the examples I made before. You first take a continuum limit, you get to an hydrodynamic description in terms of a densities and smooth fields and so on, and then you take a classical limit and you simplify the dynamics to what is standard hydrodynamics, and you miss superfluidity. Okay, suppose that I want to play the same game, first at the heuristic level in quantum gravity. And then I will show you one concrete example in group field theory in which we can take all the steps. But let's try to imagine what we are supposed to be doing in quantum gravity. So first of all, we ask what could be the relevant hydrodynamic observables in quantum gravity. Well, for example, simple averages of one body observables extensive in the number of atoms of space-time. So if there are things that that receive a contribution individually from each of the atoms of space, whatever is their exact definition, well, these are the perfect candidates for global hydrodynamic observables. For example, if the total volume of space receives a contribution from each atom of space, then the total volume of the universe would be exactly such a hydrodynamic variable. And as I said, one key hydrodynamic quantity would be the reduced one-body density. So some function on the space of data associated with a single atom of space. Now, still at the super heuristic level, suppose that I do things classically by imagining that my microscopic theory is actually GR, where the atoms are the values at each point. Okay, so the contribution from each point in the spatial manifold is my atom degrees of freedom. Well, then I have a full phase space for GR of this type with the intrinsic metric and the extrinsic curvature. I will have a classical probability density which encode my perfect knowledge of all the microscopic details, some complicated functional of the intrinsic metric and the extrinsic curvature, and the analog of a reduction to a one particle density, treating, as I said, each point as if it was something like a constituent of the space-time fluid, would require integrating over all the degrees of freedom at all points in space except one. This is exactly the formal analog of what I wrote for the one particle reduced density in hydrodynamics, knowing the atoms. Which point shouldn't matter because of different variance. So at the end I have a density, so my hydrodynamic dynamical variable will be a density function of the intrinsic metric and the extrinsic geometry at a point. So just a set of numbers in practice. Okay. So in practice, my basic hydrodynamic variable is a function of the geometric data of mini superspace. Because if you think about it, the space of geometries at a point is isomorphic to the space of homogeneous geometries, by definition of homogeneity. So if really cosmology is the hydrodynamics of quantum or classical GR, then you should expect that it is the nonlinear dynamics for such density and for the corresponding geometric global observables. So this single body density is formally analogous to a quantum cosmology wave function. It's a functional on the space of homogeneous geometries. But of course, the resulting dynamics is highly nonlinear. You expect it to be highly nonlinear because it's the result of Gauss-Graining. So it's hydrodynamics. So you expect that the hydrodynamics of quantum gravity to be some sort of nonlinear extension of quantum cosmology. And the other thing that I want to add before I go to this specific example is that this is not enough. I mean, it's not the only key point that marks a difference with quantum cosmology, because once you drop the linearity, you drop to some extent the quantum interpretation. Because this nonlinear equation for a wave function of the universe would be more in the sense of a Gross-Pitesky wave function. It satisfies a nonlinear equation, but it has no corresponding Hilbert space of states. There's no operator that acts on the wave function in a linear way to give you some equation. So it's really hydrodynamics. So the interpretation of such cosmological wave function will accordingly be very different, will be really of a statistical nature. For cosmology, I'm not making statements about the full quantum gravity. Of course, in order to make all of this defined, and I don't want even to say better defined, because this is not defined at all, you need a notion of atoms of space. But I just emphasized from the beginning that what quantum gravity approaches do is to suggest some candidate notion of atoms of space. In particular, they suggest such notions. For example, in the cases I've mentioned earlier, a fundamental quantum simplex or a spin network vertex would be the candidate for such atom. They also provide many body observables, volume operators that at this level do not yet have a proper space-time meaning or geometric meaning, because generic configurations of these objects will not correspond to any manifold at all or any geometry, but the operators are still there. You can write down operators that you expect to become geometric in some limit. And they propose some fundamental dynamics for the observables and the states. So you have at least some tentative framework where you can try to play the game of extracting the hydrodynamics. In particular, the most convenient framework is this group field theory framework, that formalism that I mentioned, because you are exactly in a situation in which you have a microscopic field theory for the atoms, you have a Fock space, you have a second quantized language for the observables, and you have a field theoretic description of the dynamics, which is suitable for doing many-body physics. I would say that if we didn't have it, we would invent it at this point, because just like in condensed matter, you start introducing second quantized field theoretic techniques, exactly because you realize that you need to control a large number of the atomic degrees of freedom to extract macroscopic properties. Here, of course, is reverse engineering, in the sense that we have it and we ask, okay, but this must be useful for this specific purpose. Okay, so we expect that the key variable will be the density over the space of data for a single simplex or a single spin network vertex, following the same heuristics I discussed in the previous slides. And you can actually show that the space of geometries for a single tetrahedron is actually isomorphic to the mini superspace of homogeneous geometries, which means that if you have a hydrodynamics for such atoms of space, indeed, the hydrodynamics will be a nonlinear equation generalizing a quantum cosmology-like equation. So this is, again, is very general. Now I give you one example. I have, I don't know, 10 minutes with 5? 5. I just have to speak faster. or skip details, which is fine as well. Okay, so we have developed a line of research in which we try to extract cosmology from quantum gravity condensates within the group field theory framework, with all the motivations I mentioned, the general conceptual ones and the very practical one, that if the universe is a condensate and you have a field theory for the atoms forming the universe, then the extraction of the hydrodynamics is much simpler. So at the very least, it will be the first case you try to see if the general framework, conceptual framework, makes any sense. Okay, so as I said, we have a Fock space with individual particles being tetrahedra. The first problem is to identify quantum states that correspond, that have some interpretation in terms of continuum geometries. And first thing to show is that quantum group field theory condensates can indeed be understood as continuum homogeneous spaces. And you write down the simplest condensate, which is the direct analog for a group field theory of the Grosspitaeschi condensate I discussed earlier. Just an infinite superposition of a gas of tetrahedra, all with the same wave function that I call sigma. And if you think about this tentative space in geometry interpretation, would be like, suppose that you have a gas of tetrahedra. You imagine them embedded in some auxiliary, spatial manifold, and you try to reconstruct the geometry of this spatial manifold from the data in the tetrahedra. And the idea is that if the tetrahedra have all the same wave function, you're going to reconstruct the same information at every point in which you tentatively embedded the tetrahedra. There's no other type of information in these states rather than the information of an homogeneous geometry sampled at endpoints, plus the possibility of sending the sampling to infinity, because this is, as I said, a superposition up to an infinite number of tetrahedra. Okay. As I said, this collective wave function can be shown to be actually a function on mini-superspace, on the space of continuum spatial geometries at a point, or the space of homogeneous geometries. Okay, so this is going to be your single particle density, which is a function on mini-superspace. Then you try to solve the second problem, and you follow again the second problem being extracting an effective dynamics for it, the hydrodynamics equation satisfied by the collective wave function. You do it, and following the standard procedures, and you obtain some nonlinear equation for the collective wave function sigma. Nonlinearity is coming from the fact that you have the interacting building blocks, interacting atoms. And this is really the GFT analog, the quantum gravity analog of the Grosspitaeschi hydrodynamic equation for Bose condensate. Literally, you don't need to know more than the first few chapters of a book on quantum liquids, luckily for me. But as I emphasized, there's no Hilbert space associated to sigma itself. There is an underlying Hilbert space for the microscopic degrees of freedom, but none associated to sigma alone. So it's more of a statistical type of wave function. Okay, so you get indeed a nonlinear extension of quantum cosmology for the collective wave function as the hydrodynamics of the underlying quantum theory. Now, if I have one more minute or 2 more minutes, then I give you a little bit more details about one specific construction. So all this was totally general. Whatever is your fundamental quantum gravity model in a GFT language, you give me your fundamental action, your fundamental quantum dynamics. I tell you what is the corresponding hydrodynamic equation. Now, we have done, of course, things more concretely in some specific models or classes of models. We start from well-studied Lorentzian model for 4-dimensional quantum gravity coupled to a discretized, what I would say, a pre-scalar field, in the sense that just like the data on a tetrahedron are not yet geometries because there's no guarantee they will give rise to any metric field. In the same way, the data we add to the microscopic description have no guarantee whatsoever that they will describe a scalar field. So at this level, there's just an additional real number that you associate to each tetrahedron. Okay? I call it phi because you interpret it as what will give rise to a free massless, in particular, scalar field. Why do you introduce it? Because you want to use it as a clock. Otherwise, it's impossible, just with the homogeneous data, to have any dynamical interpretation of the evolution of the universe. Well, there's no notion of evolution of the universe at the in this homogeneous setting at the hydrodynamic level. Then you further reduce from a generic state with a generic wave function of several group elements or spins or other algebraic data and a real scalar field, a real number, to a simplified case corresponding to isotropic configurations that basically give you a wave function that only depends on one spin, J, and the real scalar field, the real variable. You extract the hydrodynamics, as I said. You can even rewrite it in terms of hydrodynamic density and velocity. Okay, the velocity, I didn't write it here. You find some conserved quantity, which I don't go into. And you can define, thanks to the presence of this additional real variable, which is used as a clock, you can define relational observables, which are, they're defined in the full Hilbert space, in the microscopic theory. One is just the extensive quantity corresponding to the total volume, summing all the contributions from the individual atoms at a given value of the real variable of the clock. So it's like the volume of the universe at a given time. This would be the interpretation if it satisfies the appropriate equations. Okay, but again, there are expectation values in the condensate state in the full theory. Similarly, you can define something that has the interpretation of the momentum of the scalar field, and you can show it's conserved, which is consistent with the interpretation as a free massless scalar field, and even the energy density of the scalar field at a given clock time, which has, again, the right expression. And then you extract the dynamical equations, which means you have the hydrodynamic equation for the condensate wave function, then you use that to write a dynamical equation for these observables. The time derivative of the volume, the evolution of the volume, is with respect to the clock. So this prime is the derivative with respect to the real variable, which is the value of the clock, the scalar field. So you have some complicated equation. Well, you have two equations for the first and second derivative. And, well, they're pretty meaningless. First of all, however, you can show that before you even try to interpret them, if this is really the volume of the universe, well, you see that it remains positive at all times. So whatever, for all the range of values of the real scalar field, the clock, this is positive, plus with a single inversion. Which means that generically, if this is a universe, and I haven't had further confirmation of that, well, this dynamics, with all the approximations I imposed, describes a quantum bouncing scenario. There's no Big Bang. There is just, it can go towards zero, but then it will remain positive and bounce back. And then you can even show that through the same dynamics, right after the bounce, you have a primordial acceleration. And depending on more details on the model, it can even last long enough to avoid the need for an inflaton field coupled to it. So here you just have this free massless scalar field and the quantum geometric data. And the only dynamics is the fundamental quantum gravity dynamics. In this hydrodynamic description, you have a volume of the universe having a bouncing dynamics. Most importantly, you can show that in the classical approximation, which more or less is like large volumes, you recover from these two equations exactly the classical Friedmann equations, plus corrections, of course, coming from the full dynamics, provided the microscopic parameters of the theory. This mj was, maybe you didn't notice, but it was basically some of the coupling constants in the initial dynamics. that define this mj, is approximately equal to the Newton constant, so it's constant in this regime of approximation. Notice conceptually that this is if this is full quantum gravity, this is the definition of the Newton constant. Because the microscopic parameters a priori have no reason to be identified with the Newton constant at any energy scale. Then further, you can show that if you take an even simpler approximation to the condensate, so something that not only depends only on one spin, but is non-zero only for one specific value of the spin, the corresponding dynamics is basically the loop quantum cosmology dynamics, which has a similar bouncing result. But you reproduce almost exactly the modified Friedmann equation of loop quantum cosmology up to a term which depends on the initial state. So you can even set it to 0 by choosing initial conditions. Okay, so I conclude. I gave you an example in this last part of the general conceptual framework I tried to outline, and at least heuristically convince you of. But this is a concrete example in which we have some underlying non-spatiotemporal atoms of space. Generic states of the same degrees of freedom will admit no space-time interpretation. The space-time interpretation is only approximate for very special configurations. So it's not generic at all, and it's never exact. It's an example in which really a cosmological dynamics for some key observables, the one defining cosmology, arise as the hydrodynamics of the underlying degrees of freedom. Although I didn't discuss that, this whole derivation suggests a phase transition scenario, because I picked up a very special class of states, condensates. Normally you expect them to be a good approximation of the real ground state of the system if if you are in a special phase, which is a condensate phase. And there are independent hints that there may be a condensation process in these group field theory models. And then I've shown that the modified effective cosmological dynamics staying at the hydrodynamic level, so assuming that that approximation doesn't break down, is a bouncing cosmology. I didn't say much about the details of the resolution of the classical singularity, and I didn't say anything about the possible modified kinematics and dynamics of cosmological perturbations, which is where the real physics lies. The reason why I did is that we are still working on that, so stay tuned, and for now, thank you.
Maybe I'd ask you like a little bit more about the relationship with BEC physics.
Sorry, with?
With the kind of condensed matter BEC.
Sure.
So maybe the first thing would be, how would we understand the kind of an analogous parameter to the healing length, which controls the classical transition for the BEC for the quantum cosmology? And then maybe even more exciting, would there be any prospect of doing an analog experiment using a real BEC to a balancing scenario or anything like that?
Okay, so for the first question, the only thing I can say is that there's a proper study of the healing length, and is one of the things that we need to tackle in order to explore the domain of validity of the hydrodynamic approximation. We expected generically that it would be the results we obtained are relevant provided the fundamental interactions are weak. That enters also a definition of the healing length, the scattering length, and so on.
Yeah.
So in particular, this approximation to the full quantum state in terms of disconnected tetrahedra, we have no reason to expect it to be valid a strong coupling. And unfortunately, we have hints that maybe strong coupling is the right regime, as always happens. The physics is always somewhere else, from wherever you got interesting results. But that's the only thing I can say. The nice part is that the way we are tackling this type of issues is really by a work of translation. You take standard definitions for both condensates and other fluids, and you translate in the language of group field theory and the atoms of space suggested here, and you do as much as following the textbooks that you can. Be careful of what the interpretation could be at each stage. But I don't have a result about the healing length at the moment, or more generally about the validity of the hydrodynamic approximation. The second question was about the possible analog gravity experiments. And okay, my first answer is that you should ask me again after a lot of wine tonight. Then I will give you the real answer. The official answer is that that's a very interesting question, and that indeed I've been thinking about it, but not really seriously. What I can say is that I think it gives a totally different perspective on what analog gravity is supposed to be with respect to the usual analog gravity experiments. And I say it only in a few words why that's the case, why I think that that's the case. What people try to simulate in analog gravity experiments is a manifold with a metric on top as seen by excitations. And then they have the problem that the effective metric they find on the effective manifold represented by the fluid does not satisfy the GR equations, because it satisfies the hydrodynamic equation, which have special symmetries and preferred directions and so on. And it's very difficult to come up with a way out of this. Now, if I was talking to a guy doing analog gravity experiment, as I tried, what I would suggest, as I tried, was that what they should simulate is not space-time, but superspace. So the density of the fluid should not be, after some repackaging, a field like a metric or a component of the field on space-time, because they will find only space-times with preferred directions and satisfying a dynamics that depends heavily on those preferred directions. So never something like a GR dynamics. Here, we do get a superfluid density. We get the Gross-Pitesky equation for a wave function which lives on superspace. And this is entirely compatible with the limitations of analog gravity models, because superspace is a manifold with preferred directions, a given metric, a given topology, and special symmetries. So in itself, there's no obstacle in simulating the dynamics on superspace. But you have to do a little bit more abstract thinking than what they do at the moment in interpreting analog gravity models or in devising analog gravity models. So I would ask them to try to simulate, to obtain not the GR equations, but our Gross-Pitesky dynamics. And then there will be a second step, like we did, to derive some modified Einstein's equation in terms of observables. Oh, this has been recorded.
You briefly mentioned that this bouncing mirror structure allows for avoiding an interference field. Can you say a little bit more about that? Is it right that isotropy following the bouncing scenario is not a problem anymore, but flatness would be the one that we include that?
Sure. So first of all, I make the statement more precise. So we get an effective dynamics for the volume. So we look at just one observable at this stage, with the fundamental dynamics being some underlying group field theory action, which in general has interactions, and there is some, a bit of freedom, some ambiguity, and a lot of constraints of what that could be coming from the fundamental theory. Anyway, give me your action, your fundamental action for the group field theory field, and I tell you what is the effective dynamics of the volume in this specific hydrodynamic approximation. Now, what we find is that, okay, the volume has a bounce in this effective dynamics with respect to the scalar field, with respect to the clock, which is the way we are supposed to do cosmology. Then, depending on what the interactions do, the GFT interactions, the modifications of the Friedman dynamics are such that not only there is a bounce, but there is an acceleration after the bounce, an accelerating phase. And again, depending on what the microscopic theory is, a class of microscopic models, this acceleration could be long-lasting. Now, if you want, you can take the profile of the volume and simulate it, rewrite in terms of an effective theory, in terms of a mini superspace GR coupled to a scalar field. So, in a sense, the acceleration is the definition of inflation. The point is that you don't need to, in order to generate it, to couple any additional degree of freedom beside the quantum gravity degrees of freedom I have, and this scalar field that we only use as a clock. It has no non-trivial dynamics. It's a free, massless scalar field. And therefore, you don't need to twinkle with any potential. Of course, you may have ambiguities and need for, tickling at the microscopic level.
Sorry, just to clarify, the kinetic energy of the scalar field is gravitating, right? So it's not just a clock.
Yeah, that's the source of the thing. Sure, no, it's a true scalar field. It's a true relational clock. It's not an abstract time direction. It's a true scalar field, which acts as a source of the Friedman equations. I'm saying that it's a very simple one, and we don't need to introduce at that level any additional complication for the scalar field. So in this sense, we just reproduce the inflation, but we reproduce the inflationary mechanism without any inflationary model. The ambiguities could be in the GFT dynamics, for which we have a different type of constraints. So from this point of view, it solves the problems of inflation by the same mechanism. But we didn't study yet, for example, what happens to cosmological perturbations. Well, if it was not recorded, I could tell you the preliminary results. But then again, later for dinner, I'm going to have a busy night. And also, we didn't check in detail, as an answer to Karim, we didn't check in detail the domain of validity of all these approximations, in particular the very hydrodynamic description. So it could be that we start studying quantum fluctuations and we see that, close to the bounds, we're already out. Frankly, it doesn't look like. It seems that in case we may have problems at late times, but not in the close to the bounds. Well, okay, this is preliminary. Does it help?
Thanks so much for the talk. I think I understood fairly well the explanation of using the effective scalar field as the physical clock to define time. I was wondering if you could talk a bit about time, the role of time in, really before this effective level, so in the fundamental theory.
That's known?
None at all?
No? Sorry. That's why I claim it's a pre-geometric non-spatiotemporal set of degrees of freedom, from which we have the hard task of showing that space and time and geometry emerge.
The evolution in the fundamental theory, it's true there's a second Hamiltonian or...
No, there cannot be an Hamiltonian, because the Hamiltonian is the generator of the flow in time. There is a fundamental action for the theory, which is not defined on any space-time manifold. It doesn't have preferred directions, time or space directions. It's a more abstract type of field theory.
So it's more like an internal parameter in that action?
No, there's no special parameter in the action. There are coupling constants. Okay, if you want, all this is based on the fact that these pre-geometric, pre-spatiotemporal degrees of freedom have a sort of a proto-geometric interpretation in terms of discrete geometric data, in the sense of lattice gravity and so on. But it's not that there is space in the usual sense of there's no manifold, there's no smooth field, there's no metric field, and so on. If you use the Lorentz group as a group in defining the theory, you may say that in each simplex you have a sort of a fundamental local causal structure. But my point is that, you can have all those definitions, but if a generic state with the same degrees of freedom does not allow any interpretation in terms of a smooth metric or a manifold. It lacks all the typical properties we associate with space and time and geometry. Then you are not really entitled to interpret in spatio-temporal terms with confidence those seeds of spatio-temporal structures. The task will still be to extract the usual notions from those seeds. And this is what I try to show at least in one example.
Okay, yeah, that makes a lot of sense. Thank you.
It's really thanks. Actually, it's probably pretty quick because you just answered the question I was sort of going to ask there. But maybe there was just like one little bit of clarification. You did talk about dynamics at just at the group theory level, but that's not supposed to have any temporal connotation. You just mean apply the action. Yeah.
Mm-hmm.
Let me ask my other question.
If you want, I have a partition function for my microscopic degrees of freedom, and that's it. And the partition function doesn't have to be understood as exponential of minus beta Hamiltonian, because there's no such interpretation for the action itself appearing there.
You can sort of see why when you then call it dynamics, people start to think there might be some sort of time. Yeah.
I have to talk even more with philosophers so that I know which words I should avoid.
So the question, and I hope this is probably pretty quick, right? So if you're getting a bounce, so you started off by talking about Geometrogenesis, but if there's a bounce, there's no Geometrogenesis, right? These seem like opposite things. Okay. Is that right?
So I emphasize that it all depends on the validity of the hydrodynamic approximation. We have to check that in the regime of, in the range of values for the hydrodynamic observables, like the volume and so on, that corresponds to the bouncing region, we are still within the hydrodynamic approximation because of fluctuations, because of the microscopic dynamics and so on. So it could well be that, in that regime, fluctuations become strong enough that you cannot treat the system within mean field and the simple quantum states I considered. And you really have to resort to the microscopic description, maybe indicating that you are indeed approaching a phase transition, like a Geometrogenesis scenario. Or that could be true not because of the value of V or the volume, but because of the range of values of the coupling constants, which are running with respect to the same degrees of freedom. So a strong coupling, maybe that's where the phase transition occurs, and you don't trust anymore the Gross-Pitescu approximation of the quantum state. Notice that, again, let me emphasize, this Gross-Pitescu approximation is very, very special. We are neglecting totally the correlations between the tetrahedra, which will be naturally and necessarily generated by interactions. So we know it's wrong. It cannot be the correct vacuum of the theory. But everybody knows that in condensed matter. That is just an approximation that you hope is valid in some regime, and then you have to test the validity of that. We are neglecting the entanglement between the quantum states of gravity and space, and that cannot be correct if they are interacting.
Thank you, Daniele. This is a conceptual question I was asking. In loop quantum gravity, I was under the impression, especially given a previous comment here, that the manifold continues to sit there as part of your mathematical background structure. We don't throw away the manifold and quantize it in the geometric field. And in fact, the manifold goes into just helping us to define the spin network states themselves. The manifold has a particular topology, and that topology ends up constraining the Hilbert space's states. Is that the case? I was under the impression that some of the comments here make it sound as though the continuum manifold goes away and then somehow has to come back in the emergent limit. At least some of the words that were said.
So in standard loop quantum gravity, indeed you can maintain the point of view that, the manifold certainly is there in the old construction, even after you mod out by diffuse. You're dealing with the diffeomorphism equivalence classes of graphs and corresponding structures. that you may still think as living in a manifold. On the other hand, from the mathematical point of view, at the end point of the construction, the manifold doesn't really play any role, because you removed the information about where these spin networks could live by the different variants. So it's there because you kept constructing using a manifold up to that point. But there, if I just write for you the Hilbert space of the theory, which at the end of the story, regardless of how you got there, is d degrees of freedom, the manifold doesn't enter. There's no reference anymore to the manifold.
Good. So this was my impression, is the sense in which we're just no longer using it once we've gone to the algebraic formulation. But it hasn't actually left our mathematical description. It continues to sit there, at least as a ladder in building the states and constraining the state space.
It depends if you want to carry memory of how you got to a certain Hilbert space, or you just say, okay, that's my Hilbert space, and
Sure.
now what is it? In the Hilbert space, I would say two things which seems contradictory. First, there's no remnant of the continuum structures you used to arrive there. There is a superposition over graphs with conditions on the graphs and the data associated with them. Nothing else. So it's really purely combinatorial and algebra. So from this point of view, no, there's no manifold. You lost it. Unless you sort of keep the memory of how you got there. But it's, I would say, only heuristic, maybe is useful for interpreting what you're doing, but technically it's not that. There is some properties about in particular concerning the relation between states associated with different graphs, so these so-called cylindrical consistency conditions, which are again just algebraic and combinatorial conditions on the states, so they don't need to be interpreted in terms of a manifold, but they do come from the fact that you require that you add some continuum connection on a manifold. And there is an algebraic combinatorial remnant of those conditions. Those conditions are dropped normally when you go to the spin form formalism, and they're certainly dropped in the group field theory reformulation of the same degrees of freedom. Technically, they correspond to different Hilbert spaces.
Right. Good. And so for someone who was concerned with the ontology of the objects, like where are these objects, and was inclined to interpret the world substantively, I know that you and Rovelli will interpret the world relationally, so you're not inclined to a sort of substantival view. But if one was metaphysically inclined towards this view, one still has the manifold that they can interpret as still being a substance that things live inside of. Though you're correct, the physics doesn't make any direct sort of reference to it once you go to the algebraic formulation.
Okay, I cannot speak for Carlo, but I always get a little bit frustrated by statements like, okay, the manifold doesn't enter anything, you can have a compute in the theory, but you know, you still need it to make sense of the theory, or it's still there to define your ontology. It means that your ontology is not based on anything you will ever compute.
Yeah,
no, I mean, you can stick to it.
Yeah, certainly the substantivalist has a different sort of explanatory question to ask, like why hold on to this ontology given that none of our sort of experiences with the world requires it? So I think that's a great question that the substantivalist would have to answer.
Look, I mean, you're talking about manifold substantivalism.
Yeah.
I'm not particularly interested.
Sure, yeah.
In these theories, you can still debate between substantivalism and relationalism in a different sense. I dealt with the relational observables to interpret degrees of freedom of a system. The language I used somehow is very much a substantivalist language. Quantum space, or whatever replaces quantum space at the fundamental level, I'm treating it as a substance made out of atoms that organize themselves, like all substances do.
Yeah.
It's just that the observables, the questions I ask to my system, which is a substance, have to be relational because I cannot introduce any special frame or direction and so on.
Yeah, perfect. Thank you. It's very helpful.
Sorry, just to clarify, it's not that I'm not interested in the debate about substantivalist versus relationalism concerning to the manifold. It's just that here doesn't really enter because, as I said, there's no manifold. So I would have to introduce it only to carry on with the debate.
Correct, and in a sense it doesn't emerge either. There's no continuum manifold.
As I said, just like I can write the effective dynamics, so I have a dynamics for an observable in the full theory, which doesn't require a metric field, doesn't require things like this, but it behaves as an observable as the Friedman equations. Now, of course, I can say, to some extent, what I did was to reproduce an effective metric field, at least in terms of homogeneous degrees of freedom, with an effective continuum scalar field, both defined on a manifold, and recover a sector of GR with all the extra structure. But they are just used at this effective level. So in some sense, I have reproduced a manifold, a metric in some aspects. But it's the rewriting of the theory, because I need that rewriting, or maybe conceptually, because that's the way we usually think. We are used to that language. We do not have a pure diff-invariant definition or rewriting of general relativity that only uses the fundamental observables of the theory. We don't have a full deparametrized redefinition of general relativity, except special cases. So if I want to check that I reproduce general relativity, I have to reproduce it with all the extra baggage.
Hey, I just wanted to ask one question about how you were kind of understanding this Bronstein cube that you showed and the limits in it. So
Bronstein cube or the Hypercube?
Or the Hypercube, yeah. But I mean, my concern is
The
specifically
Hypercube.
with the sort of h bar goes to zero limit.
I'm not going to go back to the cube.
Sorry?
No, nothing, sorry. Stupid joke.
Are you not going to adopt limits?
Sorry, that's the question. I should just shut up.
Yeah, the question was just, so I guess, so it's really like a two-part question. So first, how do you know exactly when a theory has the correct classical limit? Because, I mean, certainly in some cases, right, when you think the h bar goes to zero limit of some quantities, right, you get a smooth limit where you see the kind of analogous classical quantity. But if you just take, kind of naively say that take the h bar goes to zero limit of the Schrodinger equation, that gives you nonsense. Right, it doesn't give you anything classical. So I guess the first part of the question is really, which quantities do you need to smoothly converge to classical quantities in order to say that you've obtained the correct classical limit? And then the second part of the question is, what's the physical significance of that operation for showing that any system that can be modeled in the classical theory is even more accurately regarded as a system in say quantum gravity? So, because h bar, as is often noted, is a constant. So what is the kind of relevant physically variable quantity that you need to change?
Okay, so first of all, it should be understood that when we say h bar going to 0, c going to infinity, and so on, these are just heuristic values. I have only heuristic value. I mean, the world is quantum mechanical. H bar is a certain number. G is a certain number. It may run, but that's a different story. So the classical limit is not h bar going to 0. Particles are quantum period, and a particle behaves classically if it is in some particular states which are very well peaked around a point in phase space, and it has small fluctuations, and it remains like that for all the evolution. There shouldn't be any. I mean, there shouldn't be an ambiguity there.
Yeah,
no, but I thought that was obvious.
Yeah. But I guess I'm just wondering what the cube is supposed to illustrate in a way, and what the heuristic is, right? So how does it help you?
Somehow the cube tells you that whatever in your all the observables or quantities in your theory that depend on h bar should become subdominant in a certain regime of the theory, or for certain states of the theory that you call classical. So I've shown you an example in which you extract first the hydrodynamics by some continuum limit. Okay, forget about that part of the hypercube. And then I took a classical limit. I didn't do anything with the constants. I considered a regime in which the volume of the universe more or less was large. In that regime, you see that the terms that depend on h bar drop. So it's a classical limit because you lose quantum effects, but you're still within the full quantum theory. You haven't taken any limit in the constants. You just consider special states and special regime of range of values of the observables, and so on, so which is what we do, right, in physics. I mean, you are a quantum object. I am a quantum object, although luckily I don't notice that.
Okay, thank you.
All right, let's thank our speaker.